Here we're going to look at topic 70, example 1, transform a quadratic function. I want to start with the concept though. So the concept here is representations of quadratic functions, and there's two things I want to focus on. First, the fact that a quadratic function can be written in the form ax squared plus bx plus c, where a does not equal 0. Right? This is important. And then I want to look here at what's called the vertex form, which is what we're going to get into in this video. The vertex form of a quadratic function is f of x is equal to a times the quantity x minus h squared plus k, and then where hk is the vertex of the problem. And that's why it's called vertex form, because we have the vertex right in there. Pretty clever. So the vertex form is useful because it highlights the vertex of the graph of the quadratic function, which is pretty obvious. All right, 70.1, transform a quadratic function. The main question, how are the transformations of the graph of f of x equals x squared related to an equation representing another quadratic function? So remember, this is our parent function. So f of x is equal to x squared. It's our parent function, our parent quadratic function. And then vertex form shows three different ways in which the graph of the function f of x equals x squared may be transformed. So first thing we have is our a value. And the thing that a does is if a is greater than 1, then our graph opens upward. So I'm going to say our graph opens upwards. If a is less than 1, it opens downwards, right? That's where we have a reflection. If the absolute value of a is greater than 1, then there's a stretch. And if the absolute value of a, let's fix that. If the absolute value of a is between 0 and 1, then there is a compression. We've gone through this before. So we have graphs that either open upwards or downwards. We're talking parabolas here. And then depending on the a value, if its absolute value is greater than 1, then it's a stretch, vertical stretch. And if the absolute value, although this is a little hard to read, the absolute value of a is between 0 and 1, then it is going to be a compression, okay, vertical compression. Next, we have the h value. Remember, these are backwards, so if we're subtracting h, there is a horizontal shift right. If we add h, there is a shift left. And then finally, our k value, this is vertical. Actually, so let's say these are right, horizontal, left, right. And then the k value is probably the easiest one to figure out. If you add k, it's exactly what you would think is a shift up. And if you subtract k, it is a shift down. So these would be our vertical shifts. All right, so that's kind of the background information or the rules that we're going to apply with vertex form. And now we're going to apply those rules in examples A and B. So let's start with red here. All right, so in example A, we have this -1/2. And what that tells me, right, A is -1/2. And I have a h value. We want to be careful here. So this h value is +2. So just think about what's going on there. That actually means h is a -2. Just be careful. All right. When you have this kind of function, the actual h value is -2. There's still going to be a shift left here, right? Because we're adding 2, but h itself is actually equal to a negative. So really, you really have to be careful with h values. And then finally, k value, we don't have a k value here, right? That would be here. That's just going to be 0. So we don't have to worry about that. All right, so the a value, a is less than 1/2. A is less than 1. A is equal to negative 1/2. So since A is less than 1, I made a mistake up here. I apologize for this. This should be up here. Let's fix that. If A is greater than 0, it opens upwards. If A is less than 0, it opens downwards. I was getting ahead of myself with the stretch and compression. So that should be greater than 0 and less than 0. I apologize for that. So going back to problem A, gotta fix this too now. All right, so A in this case is less than 0, right? Because it's a negative 1/2. So that means it's going to open downwards and there'll be a reflection. And the absolute value of A, so the absolute value of A in this case would be between 0 and 1. So that tells me that there's going to be a compression. Right, because we have that 1/2. So 1/2 is between 0 and 1, or the absolute value of negative 1/2 is 1/2. That's between 0 and 1, that'd be a compression. The H value, all right, again, this is where I can't stress enough how careful you have to be with this. The actual H value is -2. However, since we are adding that H, there's actually going to be a shift left 2 units. And then there's no vertical shift because K is 0, so we don't go up or down. And then if we look at our graph here, it's already been graphed for us. F was the parent function, f of x equals x squared. And then we can see that A means the graph went downwards, right? So it's upside down, there's a reflection. And it's kind of tough to see stretches and compressions at times. But in this case, there is a vertical compression. You can see how the graph becomes a little bit wider. Right, G is definitely wider than F. So that's where that compression comes in. And then our vertex used to be right here, and then it shifted over those 2 places to the left. All right, in example B, we have an A value of 2. We have a B value, be careful, B is actually 1. And then we have a C value of -3. All right, so let's just start with the C value because I already have the green marker highlighted. So for subtracting 3, that's going to be a shift down. So this will be a shift down 3 units. The H value, that 1, we're subtracting 1, so that is a shift. Again, be careful with your H values. That is a shift right 1 unit. And then our A values here, we know that A is greater than 0, so it's 2, so that's going to open upwards. And then the absolute value of A is greater than 1, so that tells me that there's going to be a stretch. All right, since absolute value of A is greater than 1, absolute value of 2 is 2, 2 is greater than 1, there will be a vertical shift. And if we look at our graph, so our point F, we went right 1 unit, and then we went down 3 units, so that's where our vertex is going to be. And then that vertical stretch, the stretch, think of it as like pulling the graph like from the bottom and the top. It's going to make it more narrow. It's going to kind of push it in horizontally, so it'll make it look a bit taller. And in that case, we can see that pretty clearly. So outside of that little mistake, talking about opening up and downwards, sorry about that, where I put that 1 there, it should be a 0. Really just be careful with your H values. Checking here, we have another mistake there. That should be H equals 1, not B. And this over here should be K equals -3. I'm on fire today. All right, K equals -3. There we go. So A, H, and K. No A, B, and C in this. A, H, and K. Be careful with your H values. You will have to determine what the actual H value is. And for A, like you had -2, you'll see in the next video or the third one. However, be careful whether you're shifting left or right with that. I can't stress that enough. All right, that's it for topic 70, example 1, transform a quadratic function.